Good morning to one and all. Myself Dr. Ramgopal, Associate Professor in Mathematics, Department of Humanities and Sciences, MLR Institute of Technology, Hyderabad. I welcome you all to today's session on testing of hypothesis concerning proportions. Let us recall the previous session. In the last session, we have discussed the testing of hypothesis concerning means. In that, particularly one mean and two means for large samples. And also we have discussed some problems on one mean and two means for large samples. Now, coming to today's presentation, we will discuss the test of hypothesis concerning one proportion large samples and then problems on the same. Now, here proportion. The proportion means the percentage, or we can say the probability also. The definition of probability is favorable number of cases by total number of cases. The proportion is also similar to that, and a proportion can be given in terms of a percentage or in terms of a value that lies between 0 and 1. Now, let us consider an experiment, and here we divide the outcomes into two exclusive cases, the occurrence and non-occurrence of an event. Which is, occurrence means we consider it as success, non-occurrence means it is a failure. Let us denote P be the proportion of occurrence of an event, that means P is the proportion of successes, Q the proportion of non-occurrence of an event, which is called failure. Let us consider a population and draw all possible samples of size n from that population, and now compute the proportion P of successes for each of these samples. In the notation, we have considered small p as the proportion of population and capital P as proportion of sample. So, here for each of these samples we calculate the proportion capital P, and this is called the sampling distribution of proportions. And for that sampling distribution, we can find the mean and variance also. So, the mean and variance of sampling distribution of proportions are given by mu p is equal to the proportion of a sample, and variance is given by pq by n. Now, in test of hypothesis concerning proportions, again there are different types, particularly for large samples and small samples, then one proportion and two proportions. Now, let us consider the problems on large samples and then one and two proportions. So, testing of hypothesis concerning proportions, in that I am considering the large sample problems, in that again one proportion problems and two proportion problems. Now, test of hypothesis concerning one proportion for large samples. Here again we use the jet test, which we have used in the previous tests also. That means the testing of hypothesis concerning means, one mean and two means for large samples, we have applied jet test. Here also we apply the same. So, let us consider a single population, from that draw a sample and compute the proportion from that sample. So, this comes under testing of hypothesis concerning one proportion for large samples, and the test is as follows. In one proportion problems, we consider the null hypothesis as p equal to p naught. This p naught will be the given proportion which will be given in terms of a percentage or any value that lies between 0 and 1. So, the probability, percentage, proportion, all these are one and the same. Since the null hypothesis should be in the form of equal to, here we consider the null hypothesis as p equal to p naught, and we test this null hypothesis against the alternative hypothesis, either p less than p naught or p greater than p naught or p not equal to p naught. There are three types of alternative hypothesis. So, less than type, greater than type, not equal to type, and the level of significance alpha will be given in the problem, and the most general values are either 5% or 1%. Now, the critical region, the region in which we reject the null hypothesis, region in which we reject the null hypothesis is called the critical region. So, here in step 4, we write the conditions when we have to reject the null hypothesis. Again, this depends on the alternative hypothesis. If it is less than type, reject the null hypothesis when Z calculated is less than minus Z alpha. If it is greater than type, reject the null hypothesis if calculated value is more than that of tabular value. And in not equal to type, compare if the calculated value is negative, compare with this negative condition, and positive, compare with the positive condition. So, these conditions are the same that we have used in the case of one mean and two means for large sample problems. And coming to the next calculation, here we consider the test statistic. Again, this follows standard normal distribution, hence the test comes under Z test, and the calculated value is given by Z calculated is capital P minus small p by root PQ by N. Here capital P is the proportion of sample. We have considered a sample of size n. Out of n, let us suppose there are x successes. So, the proportion of successes is given by x by n. So, capital P is x by n and small p is the proportion of population. Proportion of population will be given in the problem, that we need to check that statement itself. So, it will be given like some constant p naught. So, small p is p naught and capital P is x by n. Capital P minus small p by root PQ by n. This gives the calculated value of Z. The same formula can be rewritten in the form of Z calculated is x minus n p naught by root n p naught q naught. That means, if you replace capital P is x by n here, then by taking the LCM and simplifying, we will get this formula. Both are one and the same. After calculating Z value, let us compare this value with the tabular value and take the final decision whether to accept the null hypothesis or to reject the null hypothesis. So, these are the steps involved in testing of hypothesis concerning one proportion for large samples. Now, let us discuss an example on the same. Problem number 1. In a random sample of 600 cars making a right turn at a certain traffic junction, 157 drove into the wrong lane. So, the information given in the problem is out of 600 cars, 157 drove into the wrong lane. Test whether actually 30% of all drivers make the same mistake at this junction at 5% level of significance. So, this 30% is given. The actual statement which is to be tested is the null hypothesis. So, this 30% is our null hypothesis. So, given proportion of population P equal to P naught is 30%, which means 0.3. And next, in a random sample of 600 cars. So, size of the sample n is 600, that is why it comes under large sample. 157 drove into the wrong lane. Actually, x denotes the successes. In general, we take x as successes, then n minus x will be failures. But here, the problem is about the drivers who commit some mistake, and out of 600, 150 drove into the wrong lane, 157 drivers committed the same mistake. So, if I consider x as 157, the number of drivers who committed a mistake at a particular junction, that is x. The main thing is this x and this small p both should be matched. If x denotes the number of drivers who committed mistake, then p also should be the probability or the proportion of drivers who committed mistake. Or if x denotes the number of drivers who has driven properly, then this p must be the same. So, here out of 600 cars, 157 drove into the wrong lane. So, x is 157, and we need to check whether 30% of all drivers make the same mistake or not. So, this 30% is also about the number of drivers who committed the same mistake. That's why I can consider X as 157. So I can calculate capital P, X by N, 157 out of 600, and small p is given 0.3, then N equal to 600. So this is the given data, and now the test is as follows. The first one, null hypothesis H naught. The probability or the proportion of drivers who have committed the mistake is 0.3, 30%. We need to check this statement whether 30% of drivers commit the same mistake or not. In the question, we need to test whether 30% of all drivers commit the same mistake or not. There is no particular claim given by anyone. So hence the alternative hypothesis will be of not equal to type. The null hypothesis is P naught is 0.3 and alternative hypothesis is P naught not equal to 0.3. Level of significance is given in the problem 5%. So alpha equal to 0.05, and this is not equal to problem. So reject H naught if Z calculated is less than minus Z alpha by 2 or Z calculated is greater than Z alpha by 2. And for 5% level of significance plus or minus Z alpha by 2 values using the reference table plus or minus 1.96. Now, if you substitute all those values, x equal to 157, drove into wrong lane, n is 600 into proportion is 0.3 under root 600 into 0.3 into q naught is 0.7, 1 minus p naught is q naught. If you calculate this value, we will get minus 2.0489. So this is the calculated value and which is negative. So compare with the negative tabular value, minus 2.0489 and minus 1.96, which is less than. So Z calculated is less than minus Z alpha by 2. If Z calculated is less than minus Z alpha by 2, we have to reject H naught. That implies reject H naught. If we are rejecting H naught, what does it mean? We have to accept the alternative hypothesis. That implies accept the alternative hypothesis that 30% of all drivers do not commit the same mistake at the given junction. This is our final conclusion. Now let us see one more problem. The problem number 2. Test the claim of a manufacturer that 95% of his stabilizers conform to ISA specifications if out of a random sample of 200 stabilizers produced by this manufacturer, 18 were faulty. Use 1% level of significance. So again I repeat, test the claim of a manufacturer that 95% of his stabilizers conform to ISA specifications. So here the manufacturer gave a claim 95% of his product is perfect or under ISA specification. Now we have considered a random sample of 200 stabilizers. Out of 200, 18 were faulty. Now test the claim of the manufacturer at 1% level of significance. Here we have the probability or the proportion of successes P, which is P naught, and X, the number of successes out of n trials. And the main point is this X and this P naught should denote the same context, should be used in the same context. If X denotes defective items, P naught must be the proportion of defective items. If X denotes non-defective items, then P naught should be the proportion of non-defective items. So this is the main point we need to observe. Here you see the claim of the manufacturer is 95% of his stabilizers are under ISA specifications. That means 95% of his product is good. But in the sample data, what is given? 18 were faulty. So 18 stabilizers are defective stabilizers. Here this 95% is about good stabilizers and this 18 is about defective stabilizers. These two are not matching. So this is the main point we need to identify from the given data. Okay. So first given the proportion P equal to P naught is 0.95. I am considering this proportion of good stabilizers, and a sample of 200 stabilizers has been taken. So, n equal to 200, and out of 200, 18 were faulty. Since this proportion is about good stabilizers, our x should be 200 minus 18, but not 18. 18 defective stabilizers. So, the number of successes means 200 minus 18, 182. We have to use this value of x. If P naught is 0.95, Q naught will be 1 minus P naught 0.05, and this is our value of x. N is 200. Let us start the testing of hypothesis. The procedure, as we know, it includes 6 steps, starting from null hypothesis. Now, what is the null hypothesis H naught? The actual statement which is to be tested. Here in the problem, we need to test the claim given by the manufacturer. So, the null hypothesis is P equal to P naught is 0.95. 95% of his product is good. Alternative hypothesis. As we know that there are 3 types of alternative hypothesis: less than type, greater than type, not equal to type. But here in the given problem, we need to test the claim of the manufacturer. And one more thing, always we try to reject the null hypothesis, or our alternative hypothesis should be considered in such a way that it should reject the null hypothesis. It should be exactly opposite one. So, to prove that the manufacturer's claim is wrong, we have to consider the proportion of good stabilizers is less than 0.95. Less than type we need to consider. For example, if you consider greater than type, the manufacturer's claim is out of 100, 95 stabilizers are good. If we consider alternative hypothesis greater than 95, how can we reject that? If alternative hypothesis is greater than 95, his product is good for more than 95%. That is why we cannot take greater than type. To reject the manufacturer's claim, our alternative hypothesis must be less than 0.95. If we prove that out of 100, good stabilizers are less than 95, we can reject his claim. So, it comes under less than type problem, and the level of significance is given 1%. So, alpha is 0.01, and the critical region less than type problem. So, reject H naught if our calculated value is negative corresponding value of Z alpha, negative Z value, and in the case of alpha equal to 0.01, this minus Z alpha is minus 1.645, minus 2.33. So, here for 1% level of significance, the negative tabular value is minus 2.33, and we can cross check with this. Let us substitute the values: x 182 minus 182 into 182 minus the proportion 0.95 into, there are 200 stabilizers, under root 200 into 0.95 into 0.05. So, this gives the value minus 2.5957. Now, if you compare these two values, minus 2.5957 and minus 2.33, clearly it is less than. So, Z calculated is less than minus Z alpha. Hence, the condition is satisfied. So, reject H naught. That means we reject the manufacturer's claim that 95% of his stabilizers are not ISI specifications. That means accept. If we are rejecting H naught, it itself means we have to accept H1. So, less than 95% of his product is ISI with ISI specifications. Now, coming to the summary of the present session, we have discussed test of hypothesis concerning proportions, particularly for large samples and one proportion, and problems also. In the next session, we will discuss about the test of hypothesis concerning two proportions for large samples. Thank you very much.